Hello everyone. So we already have started the sensor physics part, and in our last lecture we have seen what are the different capacitive sensors. We have given some basic idea about capacitors, how capacitor work, and then have given you some examples which shows that how we can actually develop sensors using capacitors. So as far as the capacitive sensors are concerned, I mean it's again a very vast field, but to give you the basic idea about the capacitive sensors, I have covered the bare minimum, the kind of concepts needed for someone to understand what is capacitive sensor. So today we will start a new kind of sensor, which is thermal sensor, and we already have taken a lot of examples already as temperature sensors in many of our discussion previously. So it's now time to understand what is the physics behind that temperature sensor, what are the different aspects that one should look into when they develop or fabricate temperature sensor or work with a temperature sensor. So to begin with, let us start with a situation or a case where you have an object and then a sensor, a thermal sensor or temperature sensor is attached to it. Okay, so the temperature sensor is now attached to an object, and the other side of the temperature sensor is exposed to the environment. So this is a simple situation, and we would like to understand what are the different consideration that we may take in this case. So to make it more easier for us to understand, we have drawn a schematic, or you may say electrical circuit equivalent of this particular situation. So where we have taken as object, and then there is a sensor, and then there is environment. Now between the object and the sensor there is an interface, and there will be some sort of thermal resistance between the sensor and the object. That thermal resistance is given by R1, which is equivalent to an electrical resistance. So what is thermal resistance? Thermal resistance is the kind of phenomena which restrict thermal energy or heat energy to pass from one side to the other side or pass through a certain media, which is equivalent to the electrical resistance. So for that matter, any sort of resistance indicates that there is some certain sort of obstruction, or there is certain sort of resistance that actually doesn't allow the energy to pass from one side to the other side. So it's same here as well. Then you will also find there is certain sort of thermal resistance between the sensor and the environment, which is given by R2. Now almost in each material you will find that there is a tendency of storing the heat energy once you heat up that material. That extent of storage may vary from material to material, but they store certain sort of heat energy when you apply heat energy to that material. So obviously sensors are also made of different materials, so it will have certain sort of thermal storage capacity, and that is given by that is indicated here by a capacitor. Okay, so this capacitor shows the thermal storage capacity. Okay, now one may ask that why we have connected the capacitor in parallel to this line. So this capacitor may also be in series with this. For example, this is resistance, then capacitance, then again resistance. Why we have chosen this model rather than this model. So again, this is not very complicated, because both the thermal current that is passing from object to sensor to environment and the storage is happening in parallel. So it is not like when the thermal current is passing, it is getting stored and then again passing. It's not like that. So if you try to understand the entire process physically, you'll get to know that in this case, it's better, or the most suitable assumption would be to connect the capacitor in parallel to that, right? So the R1 and R2 are two thermal resistances, and then we have a capacitor connected to it, which is a thermal capacitance. So please remember, in this case, all resistance and capacitances are thermal resistance and thermal capacitance, not an electrical resistance and electrical capacitance, but they are equivalent to an electrical resistance and electrical capacitance. Now, why we are doing this? Because if you convert the entire system to an electrical equivalent, it becomes much easier for us to understand the phenomena. Okay. Now, if we consider that the thermal energy flow from object to sensor is equal to the energy outflow from sensor to environment, which in ideal case is possible. So what we are considering in this case, the energy, the thermal energy that is passing from object to sensor is same as the outflow between object and environment. Then we can write TB minus TS divided by R1. In this case, TB is nothing but your voltage equivalent. So for example, if you consider these two as a voltage, then the current will be, for example, if you consider VB, this is Vs, and this is R1 is the resistance, electrical resistance, then your electrical current would be VB minus Vs divided by R1, right? So the thermal current, which is equivalent to this, can be given by TB minus TS divided by R1, which should be equal to TB minus T0 divided by R1 plus R2, because between object and environment there are two resistance present. Okay. So one may consider that the R2 is much higher than R1, and then they can neglect R1, but that assumption we will take later. First, let us take R1 plus R2 in this case. Okay. So your equation in this case will become that the current due to TB minus TS divided by R1 is equal to TB minus T0 divided by R1 plus R2. Now, this is the equation based on the consideration that we have taken, that the thermal current between object and sensor is equal to the thermal current between object and environment. Then you do some mathematical arrangement. So your TB minus TS you have taken, and then you take your R1 in the right hand side. So it will become R1 divided by R1 plus R2 into TB minus T0. Then you may take TB, take both the TBs in one side. So TB minus TB into R1 plus R2 is what you can see here, and then you take TS into the right hand side. So it will become TS minus T0 into R1 divided by R1 plus R2, right? Then you may take TB common from both these terms. So TB into this term will become, if you take TB in common, so 1 minus R1 divided by R1 plus R2. So this is TB into R1 plus R2, and there R1 plus R2 minus R1, right? Then R1, both of these got cancelled. So it becomes R2 divided by R1 plus R2. That is what it is written over here. Okay. So then this will become TS is equal to TB into this plus, because you will take this to the other side, R1 divided by R1 plus R2 into T0. This is one expression. Or you may find this equation if you just neglect these two steps. From here itself you can directly come to this step where your TS is equal to TB minus R1 divided by R1 plus R2 into TB, this term. This will go to the other side. So, it will be plus R1 divided by R1 plus R2 into T0, right. So, this is another expression from the same thing. Even you can neglect these two steps. Okay, in this step the Ts is given in terms of Tb and T0, and now we are also taking this particular step and we will see whether we can further simplify this or not. So, let us take this. So, your Ts is equal to Tb minus R1 divided by R1 plus R2 into Tb plus R1 divided by R1 plus R2 into T0. Now, from here if you take R1 divided by R1 plus R2 in common in both these terms, then it will be Tb minus R1 divided by R1 plus R2 into Tb minus T0. Now, in this case your Ts is equal to Tb minus delta T. So, this can be taken as delta T into R1 divided by R1 plus R2. Delta T is the temperature gradient between the environment and the object. So, it is very clear, if there is a temperature gradient between object and the environment, then your sensor temperature is not equal to the object temperature. In fact, your sensor temperature will be always less than the object temperature, because it is Tb minus some value if there is some gradient. And if you look at this situation, you will figure out that your R2, that is the resistance between the sensor and environment, is much higher than the object and sensor, because object and sensor both are in contact. So, the thermal resistance between object and sensor is much less than R2. So, your R1 is much less than R2. If you take this assumption, then this particular expression will become Tb minus delta T R1 divided by R2. So, this is the relation between object temperature and sensor temperature. Ideally, both the temperatures should be equal, but in here you will find that your object temperature and sensor temperature is not equal if there is a delta T present. Now, to make both the temperature close to each other, your R1 by R2, this ratio should tend to 0. What does that mean? That means either your R2 should tend to infinity or your R1 should tend to 0. Then only the entire expression can tend to 0. Now, R2 tend to infinity means that there should be a high decoupling the environment, and the coupling between thermal coupling, of course, in this case, and the thermal coupling between the sensor and object should be very good. So, if the thermal coupling between object and sensor is very good, then you will find that your sensor temperature is more or less equal to the object temperature. So, this is something that one should achieve when they are developing temperature sensor. One is the coupling between the sensor and object should be very high, and the decoupling between the sensor and environment should be again very high. So, here coupling and decoupling means thermal coupling and thermal decoupling. Okay. Now, so far what we have discussed is a static condition. Static condition meaning we have taken that entire process is not changing with time. But for a dynamic condition, that is when the surrounding temperature changes with time, or the sensor temperature is not yet stabilized after coming in contact with the object. If the situation is this sort, then in this situation you will find that the incremental amount of transferred heat, that is dq, between the object and sensor, that incremental amount of transfer heat is proportional to the delta T, that is the gradient between them. So, from heat transfer it is very clear, right? You already have studied heat transfer in your previous classes or previous courses. So, if the thermal gradient is very high, definitely the heat transfer will also be very high. So you can say that this incremental amount of transferred heat dq can be given by alpha 1 into Tb minus Ts into dt, where alpha 1 is thermal conductivity of sensor and object, and Tb is the object temperature, Ts is the sensor temperature, right? And the absorbed heat in this case dq can be given by m into c into dt. So in this case, m is the mass of the object, c is specific heat, and dt is the change in temperature. So if there is no heat loss, if you don't consider any heat loss, then obviously your R2 is infinite, because heat loss can only happen between the object and environment. So if there is no heat loss, then entire heat is actually transferred to the sensor, or there will be heat transfer between sensor and object itself, and the absorbed heat also will be, whatever transferred will get absorbed by the sensor itself. So in this case, your dq and this dq will be equal. So you can write alpha 1 Tb minus Ts dt is equal to m into c into dts. Take the dts in this side, or you may consider or taking Tb minus Ts in this side, rearrange this equation, and then you will find dts divided by Tb minus Ts is equal to alpha 1 dt divided by m into c, right? So if you further rearrange it, it's like dts divided by Tb minus Ts is equal to dt by tau t. Tau t is nothing but the time constant. So time constant in this case is mc divided by alpha 1, or you can write m into c into R1. So in case of electrical circuit, the time constant is Rc, right? Resistance into capacitance. So it's similar here. This is the resistance, and m and c is what is the quantification of your thermal heat storage, right? So this is the time constant associated with the temperature sensor, and if you solve this particular equation, you will find Ts is equal to Tb minus delta T e to the power minus T by tau. So this is the equation that you get from this. Therefore, Tb is equal to Ts if your delta T is equal to 0. If your delta T is not equal to 0, then Tb will never reach to Ts. So this is the dynamic condition associated with the thermal sensing. So there are three take home messages. The first one is sensor temperature is always different from the object temperature if your delta T is not equal to 0, that we already have seen. And then for most efficient performance, thermal coupling between object and sensor should be good, and thermal coupling between sensor and environment should be poor, that we already have discussed. Then the dynamic condition in thermal sensor follows an exponential relation that we have seen just before this slide, that there is an exponential relation associated with that. So we will now discuss the dynamic condition in greater details in our next lecture. So in upcoming discussion, we will continue our thermal sensing discussion, and we'll see how the dynamic condition is actually influencing the entire thermal sensing concept. Thank you.